Let's get to our most important topic here, the introduction of a new calculus idea, the definite integral. The first thing we saw when we started analyzing the areas was that as we increased the number of rectangles, the estimate of the area became more and more accurate. Well, as soon as we see that, then wouldn't it be good to use the number of intervals or number of rectangles that would go off towards infinity? Well, that's exactly the kind of question we asked earlier in the course. Let's take the limit as n, which is the number of intervals or number of rectangles, and ask, well, what happens to those sums? What happens to the area estimation as we get closer and closer, or use more and more intervals that are smaller and smaller? And we notice here that as n goes to infinity, when we're talking about the interval size, we're talking about smaller and smaller intervals. Or narrower and narrower intervals, subintervals, I guess. So we can use a few rectangles and have big delta x's, or we can use lots and 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 lots. You get the idea of very tiny intervals, and there's a trade-off between the number of intervals and the interval size. Now, we would call this limit here, this idea of building a Riemann sum of functions. Again, we still see that same pattern of height and widths. The only new part that we've added here is the limit. So we would call this the definite integral of the function from a to b. And here's the brilliant part of it. It is equal to, not an approximation anymore, by the time we include this limit, we've computed the Riemann sums and then used more and more intervals and seen where that value ends up. That calculation will give us the area exactly underneath the curve. Little fine print here. When f is a non-negative and continuous function. Let's talk about how we would write this out. So definite integral is the phrase we're using right now. And the definite integral of a function, so there's our function, between x equals a and x equals b, so this is our start x, and there up there is our ending x. And the dx here is a translation from the delta x in our sum of f of xi's delta x's. Xi minus 1. Let's put the left rule in there. Oops. So when we had that same form, f of x times delta x, the definite integral is inspired directly from that same form. And in fact, the sigma here, the summation symbol, is a Greek S, to one way of speaking anyway. And this integral symbol is meant to look like an S as well. It's meant to be a stylized S. So let's just, erase that here for a second. Odd, there we go. There we go. So we're literally translating between the summation notation and this new idea where, again, the only change between the basic sum and the definite integral is that limit. We use a lot of intervals, or we ask what happens if we use an infinite number of intervals in the sum, and that gives us the definite integral. But again, that same basic structure to the definite integral. The nice thing about the definite integral notation is it makes it very straightforward to write out some kinds of ideas anyway. We don't know how to calculate it yet, but we get some very easy expressions for areas under graphs. So I don't know what this graph looks like. Actually, you should if you've done your homework, because this is very similar to an assignment problem. This is a graph that looks a lot like x but adds cos x to it, so it'll be some kind of oscillating function like this. And between 0 and 4. This is where it gets a bit dodgier. That'd be about pi, let's say there. So this area, we would have no idea what that would calculate out to be with the tools we have right now. However, we can write it out in principle. That area that we just sketched out there, well, it's the area that's underneath the graph f of x, which is x plus cos of x, times delta x's or dx's, and the integral is from 2 to 4. Whoops. And I just realized it's 2 to 4, not 0 to 4. So let's break that off here. 2. There we go. So that area we could write out as the integral of x plus cos of x times dx, or we would just say dx, from x equals 2 to x equals 4. And that's it. We very quickly have a relationship now between an area idea calculation and a notation for it, and that's going to be crucial moving forward when we try to figure out a way to evaluate these integrals. Now, just as a quick follow-up before we get into how to calculate those, let's just make sure that we actually have a single answer for these things. We defined the definite integral, and we did it using the left-hand sum. Well, what is special about the left-hand sum? Not much, actually. One of the questions we might wonder is if we use the right-hand sum, in other words, we said let the integral from a to b of f of x dx equal, so this is our definition here, not x, let the number of intervals n go to infinity if we're adding up f of xi delta x from I equals 1 to n. That's our right-hand sum here, with n intervals in it, and then we're adding this limit out front to turn it into the integral. So if that was our sum, should we get the same thing as if we did the left-hand sum? Well, here's an argument, at least based on an example that might explain why this is the case. Let's take a look at a simple example like 2 to the x. And what we're going to do is see what the difference between these two estimates is, and see would the left and the right be equivalent if we let the number of intervals get larger and larger, or are they going to get two different answers? Let's see how that might work. All right, and this helps if we do a little sketch. So we're going to go from 1 to 3, and that's going to be x0 and x1 and x2 and so on, all the way up to xn. xn minus 1 is the last one. That's how we're going to build these things. Oops. So the left calculation with 2, well, let's just do that out. We would have 1, 2, and 3. And what do we do to calculate our estimates? The left-hand endpoints would be 2 to the 1 times 1 is our delta x plus 2 to the 2 times 1. That's f of x0 times delta x plus f of x1 times delta x. Meanwhile, the right estimate is going to involve, on this interval, we take the graph back from 2 and we take the graph back from 3. So we would have 2 squared times 1 plus 2 cubed times 1, same idea. Now it's f of x1 delta x and f of x2 delta x. But in any case, when we take the difference, let's do that down here, left of 2 minus right of 2, we're going to see some great cancellation happening. That cancellation is going to look like we're going to have 2 times 1 plus 2 squared times 1. There we go. Minus 2 squared times 1 plus 2 cubed times 1. And at the end of the day, we're going to have some cancellation. That term and that term cancel. And we're left with 2 minus 2 cubed. And they all have a factor of 1. I'm going to keep that out there because it's going to play a role. Let's take a look at the next ones. And we're going to draw them out immediately. Minus right of 4. The points that we'd see on that interval would be 1, 2, 3, 1.5, and 2.5. And when we do the sum, we get 2 to the 1 times the interval size a half, plus 2 to the 1.5 times a half, plus 2 to the 2 times a half, plus 2 to the 2.5 times a half. That's the left rule, left-hand sum. There we go. And we're going to subtract from that. Well, the right-hand rule is going to use the same points, just starting at the 1.5. 2 to the 2, 1/2, plus 2 to the 2.5 and a half, plus 2 cubed times a half. So we've done that, minus the right-hand sum with 4 intervals. And again, we see this great cancellation. 2 to the 1.5, oh yeah, we've got 1 in the right. 2 to the 2, have 1 in the right. 2.5, yes. And so all of these interior points disappear, and we're left with 2 to the 1 times a half, minus 2 cubed times a half. That's the cube there. Or 2 minus 2 cubed times a half. All right. Now let's see if we can generalize this to the n case. I would argue from the previous examples and the expected cancellations and the expected cancellations of the common terms, what are we going to get there? We're going to get, well, let's just flick back. Whoops, not that button. Sorry. When we go back, we're going to see, it's here, there it is. We're going to see 2 minus 2 cubed times this number here, but what was that number? That was just delta x. What was that number? That was delta x. So we're going to see always the first value, the first height, minus the last height times delta x. But where did delta x come from? Delta x came from b minus a over n. So in this case here was 3 minus 1 over n, or 2 over n. And if we chain that out here, we're going to have 2 to the 1 minus 2 cubed times 2 over n. And if you look at all these terms, that, and that 2 there are constant. The only variable n here is in the denominator. And so if we ask our final question here, what happens if we take the limit as n goes to infinity? Well, the limit as n goes to infinity of left of n intervals minus right of n intervals is going to equal 2 minus 2 cubed times 2 over n. Whoops, we need that limit out front. Keep it around. And pretty clearly, this is the only thing that's moving, and it's in the denominator. So that limit is going to equal 0. What does that tell us? Well, n is the number of intervals. And as that increases, well, if the difference between, let's do this in 2 stages. There is a difference between the left and the right-hand sums, absolutely. No matter what number of intervals we pick, there's always some difference between them. But the difference between them, the right and left rules, or the right and left sums heads towards 0, well, if their difference heads towards 0, then that means that left of n is equal to right of n in the limit as n goes to infinity. So these two things are the same, which implies that it doesn't matter if they give us the same value no matter what, then it does not matter which one we use to define the definite integral. We can pick one if we like. Turns out it's not going to matter. In most cases, we're not going to think about it too much in terms of the details of left and right. But at the end of the day, both of those sum approaches would produce the same value if we were to ask what happens if we get the real integral, the exact area under the curve. Both the left and the right will give us the exact area under the curve so long as we're able to let the number of intervals go off to infinity. And that's enough theory for now. We'll see some other examples moving forward.